Get started. I wonder if I can close that. I'm going to close this tab. If it kills the Zoom meeting, I'll just restart it, so be patient. Oh, it didn't. Excellent. Cool. And I will, let me save this. We'll go look at that in a minute. Shrinkify that. All right. So there's the work plan for today. A little bit modified from what I'd normally do. And the computer is not responding to input. There we go. That is a lot of entry chimes. It's 11 people. That's actually pretty close to the full complement. So I will start. The recorder's running because that little red dealie's on up there. So good evening, everybody. The scheduled topic for today is Lesson 5 Pipeline Hydraulics. However, based on this morning's class, there was a great desire to see Exercise 2. Many of them were confused or didn't understand where to start. So I think I will do that for you all right now, unless there's a huge desire not to. And then we can pick up the lesson if there's enough time left. I don't think it'll take an hour and a half to do Exercise 2. So I've done a little bit of homework already. And so what we're recording right now is going to go here, and the morning recording is there. There's no point in clicking on them right this instant. They're not uploaded yet. And then some older stuff. And that way we'll at least have Exercise 2 mostly completed, so you can refer to that. I think it's actually due tomorrow night. So there is enough time left to complete it, especially if I show you how. So unless there's a huge protest, I'm going to show you how. And let me get the chat up so that you can protest. It's empty, so there you go. So let's go to Blackboard. Now I want to do a new tab. No, actually I want to go to Firefox because Blackboard doesn't play well with Safari. So log in. Good lip reading. I was saying my password quietly, so you all probably you now know it if you can lip read. And God, oh, there's the annoying. Hi, would you like us to go kick your dog? No, thank you. Evening is section 1. And lesson collection. Oh, you don't even have a lesson 5. That's kind of embarrassing. I will fix that in a minute. Actually, I'll fix that right now. Sorry to do this to you. Let's go ahead and first put the lesson there. So my experience with Blackboard as an instructor, so it's different than your painful experience as a student, is sometimes it's simply you give it input and it doesn't do what you've instructed it to. So it's kind of like having a pet cat. I got 3 of them, so I'm kind of used to it. But should be there now. Yay. And if we take the content links, it's going to go back to the web page But there was another reason for going here, which was not. See, I actually did a go back thing and it ignored it. So here was our exercise 2. Let me check that it's due Wednesday, because it was, yeah, it's due Wednesday.
The homework for the exercise 2, I thought it was due Sunday. So if you like explain it and I see that I like made a mistake, can I return it in?
Yeah, I don't see why not. Let me go ahead and make a change to something, not the due date. Edit the actual exercise. I'm going to try to make it for multiple submissions.
Okay, sorry. It's just because it was due on Sunday when I saw it for the first time.
It allows multiple attempts, so as long as you should be able to do it again. But go ahead and email me if it doesn't work for you. It allows 2 tries.
Okay.
Or at least the interface says it allows 2 tries. Blackboard does whatever it damn well pleases. So let's go look at the actual exercise. And I know most of you know what the task is because you've been struggling on it. Oh, it's actually in go slow mode. 6:30 at night. Oh, everybody in my neighborhood's streaming their evening videos, so we'll be lucky if we hold the call for a whole hour. So here's the homework assignment, and this is the image that you're working on, and we're trying to produce XYZ information to draw a topographic map of this area. And by XYZ, we want to know the X coordinate, the Y coordinate, the Z coordinate of each of these numbers. And it has some steps to follow. So what I've done is, let me get out of here. Go get back to the server. And whether we go through lesson 5, 1, 2, or 3 is irrelevant. We'll go through lesson 5. We can go to the software field here and choose the old style archive because it turns out I don't actually have it directly connected. And there's a program in Windows called G3Data, a tool to digitize, produce XY coordinate files from a JPEG or PDF, used to take images from graphs and documents, manually digitize, and produce reasonable facsimiles of XY relationships, blah, blah, blah. For the Mac users, if there are any, in the wine rack, there is a G3Data application bundle, which will work on a Macintosh unless that Macintosh is running Catalina or Big Sur, the 2 newest operating systems. I just downloaded the Macintosh one because I'm running in a Mac now. I'm going to try that to do the digitizing so I can show you how. If it fails, I'll just go ahead and launch a Windows application. But on my computer, that's an ordeal, so I'm trying to avoid it. So the path to where we are here is Atomic Kitty ddns.net software. And so pretty much if you just go to the main server and click on software, it brings you to this page, and go to the old style archive and then work your way through that. Or use whatever software that you like to use for making topographic maps. He says with a little bit of a chuckle because most people don't do that. So there, okay, so we got the software. So I don't need the web browser big anymore. I'll put that one down there. And I've actually downloaded the map, and I'm going to move it to my desktop for a reason. Excuse me for a minute, I have an annoying cat. You're going in the cage, okay? First, say hi to everybody. Hi, everybody. That's Nico the cat. I have a place to put him. Come out if you want, Mercy. Apologize for the brief interruption. Let's continue. So I've moved the file onto the desktop. On my computer, downloads, go to a directory named downloads. Most of the time I just leave stuff there because I intend to destroy it. In this case, we put it on the desktop. Let me shrink that, and let's look at the map. So you'll see this looks different than what you downloaded. And that's because just before class, I downloaded it and I went into a graphics manipulator and I put these little codes next to each of the numbers. So E1, E2, E3, E4, E5, E6, and so on up to, I think there's 64. So I didn't notice these ones along the bottom till later. What those little codes represent is the order that I'm going to make the measurements to get the XY coordinates for each location. I've also drawn a red arrow here to correspond to the x-axis. It's 1,100 feet long, and a red arrow here to correspond to the y-axis. It's also 1,100 feet long, and that's used in digitizing to get the XY coordinate systems from the map reader to work. You don't have to draw those arrows. It's useful to put the marks where they're supposed to be. So now let's go ahead and try to run the Digitizer. Let's see if there's anything else about the picture I should comment on before I go. No. So everything about the picture is there. I just got to remember to get these corners. And I also went ahead and pre-built a spreadsheet for putting the data in. Now I'm not going to manually put it in, but this would be how you would do that if you did it by hand. Like if you were using a ruler and you went over to, in this case, E08, and you measured however far that was in inches, and then you know how long 1,100 feet is in inches, and then you measured how high that was, you would enter that x coordinate, that y coordinate, and that height of 69 into this table. So once you have the xy coordinates, you can do the z's later after the fact. Okay, so let's go ahead and get let me get that shrunk. Keep this annoyingly in the way for the time being, and I don't think I need this open. I do need to go find the digitizing software. There it is. This thing up here at the top is really annoying. Okay, I think I'm back in control of my computer again. I'm going to extract this tape archive, and hopefully this will work on my Macintosh. If you have a PC, you don't have to go through as many steps to get the software to work. You just download it from the internet, follow the instructions, and it works. This is a very old program. Oh, that's not a good sign. This may not run on my Macintosh. It's going to give me some garbage about security, and that's normal. Or it's just going to stall, which is also normal. You sure you want to open it? Yes. Yeah, it failed. Okay, we will delete that. Delete the tape archive. So G3 data apparently doesn't work with Mojave anymore either. That's an Apple thing. Apple has intentionally gone out and destroyed their operating system so that older programs don't work, so that you can buy the Apple equivalent, which does not exist. So plan B is to run my Windows copy, which I have right here. So I'm going to run it from Windows. So what's going to happen when I double click on this, it's going to start a Windows operating system. That's going to take some time, and I'll talk and stall while that time is being taken. So what's going to happen when this all gets loaded up is I'm going to open the document, the picture, in the digitizing software, and then I'm going to digitize it, and what I'll get out of that is a file of X and Y coordinates, and I'm going to visit each point in the picture in the order that I've labeled them, so that each row of the file corresponds to the E01, E02, E03, and so on. Then after the fact, I can add the, oh, that's a really pretty picture there. I can add the elevations myself. So my password is so there we go, and here's the another G3 data shortcut. I'm going to let this thing do its spinning beach ball. Okay, so it's now open to the program. What we want to do is go to the graphic file and find the correct one. That's the local desktop. On my computer, I have to go to the network drive. Ooh, that's bad. That's a sign of an imminent crash.
You said earlier that this particular tutorial you're not going to upload, but you went over this in this morning's class, and later on you're going to upload this, basically the same little tutorial.
I'm uploading what we're videotaping right now. Okay. So we'll be uploading it. Now everything's different on your computer, but on my computer, the file is right there.
So.
Okay, so the next step, currently the image scale is set to 1. If we open it at image scale 1, it's going to fill the screen and be a little bit hard to manage. I only know that because I've used this before, so I'm going to put it at about 0.4 and see what happens. And if I don't like it, you can close it and reopen it at a different scale. You can't change the scale once it's open that I'm aware of, because it's a computer and it wants to make you kill yourself. So that was probably a wee bit too small. So let me go ahead and close, and I'll restart it. And unfortunately, I have to go through the find everything path again. So 0.4 was too small. Let's try 0.7. Of course, that'll be too big. Maybe not. Oh, that looks about... Okay, that's a good size. I can almost read everything. All right, so we've loaded in the file. G3 data only works well with JPEGs and PDFs. In theory, it should be able to do a PNG, but doesn't do a good job on it. So if you have to convert your image, convert it to a JPEG because it can read those the best. So now what I want to do is I want to tell the computer program that that location where the crosshair is 0. This location is 1100 in the X direction, and 0 in the Y direction. And this location is 1100 in the Y direction, 0 in the X direction. And then I can systematically go to each of these points. And when I get to where I want it, I hit the mouse button, and it will record the XY coordinate in the actual units on the map. So unlike Acrobat Pro, it's not doing it in inches, and you have to do the conversion. So let's go ahead and get started. So the first is we want to set X1 on the X-axis. So I'm going to set X1 right there. And you see in the zoom area, it has a little dot to help you zoom in. It has a greater level of accuracy than we need. So my X1 value is 0. Now I'm going to go to X2. And I'm going to set that to 1100. Then I'm going to go to Y1, set that to 0. Then I'll move up to Y2, set that to 1100. And we're now ready, and it has all the information. And as the cursor moves around, keep your eyes up here in the processing information field. And it's showing that, for instance, a point E27 is at 1406 feet in the X direction, 844 feet in the Y direction. We come here, E20 is at 966 in the X direction, 513 in the Y direction, and so on. And we have the ability to have it record that. First thing I'm going to do is going to remove all the points because there's one that's already stored that I don't want to keep. So now it's recording 0, and we'll get started. And so we go to point E1, click it, and it's recorded. Point E2, E3, E4, E5, E6, E7, E8, E9, E10. Once you figure this out, it's so easy even a caveman can do it. E12, E13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So part of the key is to pre-label the points you're going to mark so that you can follow some sort of sequence. 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, and then the ones I forgot, 62, 63, and 64. So now we've stored everything. I want to export the data to a file, and I'm just checking where it's going to put it. It should drop back on my desktop. It's quite stimulating when that noise happens. You're not expecting it. And then I'm going to click on Export Point Data. And the file's there. We can verify that because it should have put it on the desktop. Oh, I hate it when it does that. That is not helpful, computer. There it is. There's the data. Let me get back to that other. There we go. So we're done with the program. If you're like me and you don't want to do a restart, you want to go check the file. So let's open it with a text editor. And there is our file in feet of the x, y, and z coordinates. And so we can grab this, hit the copy, go to our Excel file, why does it do that? I know I had an open Excel file, but it doesn't show it. There we go. Paste. Oh, and except for this extra line space. So we have a little work to do because we have to move all those together. So that's a consequence of the APIs not being compatible, which is also pretty typical. Back in the early days of PCs, they got together in a secret room and said, what can we use to generate billable hours? And this was a very effective way because we're going to spend a minute or two doing this. It could otherwise be doing useful work just to get everything formatted correctly. The other thing you'll notice I'm doing as I'm sliding these up is that each of them is only a single cell. I haven't actually parsed the data yet. And I never had an appreciation for graphical interfaces. I've always hated them to some extent. But this is a little easier than doing it in a text editor, so I won't complain much more, other than using it to So first I'm doing is just grouping things, and then I'll move the groups closer to each other. I'm a little too lazy to actually write a quick script to take care of the line feed issue. It's a consequence of the Macintosh, because Macintosh uses a different hidden character for line feed and new line than any other operating system in the world, I think. I even think that that real Unix, grown-up Unix, not the Linux stuff, does it the same way as everyone else too. There we go. So I think you get the idea. What I would do when I get these done, I'm going to complete this, is I will next run a tool that will split these cells by the blank space and turn them into two. No, 99999. I'm glad it's only 61 fields. So if it was 600 entry points, I would write a script to do this. There's no point doing it by hand with that many. Well, there is a point. If you are being paid by the hour, by all means do it with pencil and paper, because you'll make more money. And the only reason I'm even putting it in the spreadsheet is just going to make it easier to enter that Z data. And there's always a little frustration involved because you don't want to clobber your data. If we clobber something, well, actually it's in a file, so it's not the end of the world. We don't have to do the digitizing over again. We're getting close. All right, now all we gotta do is just get this bundle, pull it up. Last bundle. And something didn't line up. E63. Look at my picture. Oh, there is 64 items, so that's actually a good check. Let's see if it'll pick up the pattern. It does. All right, our next step is to take all that, and we need to split on the white space. So there's a tool called let's see, data text to columns, and it's delimited, and the delimiter is a space. Done. So now we have our x and y coordinates, and then we have to go back, bring up the picture, and work our way through the worksheet to enter the z coordinates. So 1, 2, 3, and 4 are all 70s. Five is a 67. So 5. So 5 is 67. 6 is 68. 7 is 69. 8 is 69. 9 is 68. 10 is 69. 11 is 69. 12 is a 70. 13, 68. 14, 67. 15, 68. E16 is a 68. E17 is a 66. E18 is a 67. E19 is 69. E20 is 68. E21 is 69. E22 is 67. E23 is 64. E24 is 65. E25 is 69. E26 is 69. E27 is 65. E28 is 65. E29 is 62. E30 is 68. E31 is 64. E32 is 61. E33 is 66. Oh, E33, if you double the index number, you get the correct elevation. How interesting. So E33, E34 is a 69. E35 is also 69. E36 is a 68. E37, 63. E38, 62. E39, 60. E40, 62, E41, 69, E42, 67, E43, 62, E44, 60, and I can still read that, barely. E45, 68, E46, 63, E47, 61, E48, 60, E49, 59, E50, 59, E51, 67, E52, 61, E53, 59, E54, 58, E55, 63, E56, 61, E57 is 66, get your kicks on Route 66, E58 is 60, E59, 26, E60, 26.5, E61, 27, E62, which is down there on the bottom, is a 70, E63 is 69, E64 is 71. So don't need the picture really anymore. There is my XYZ data. So the next thing I want to do is I'm going to need to put it into a format that I can upload. So we'll do that right here. And just kill off my notes to myself. So there's the data upload. It looks like it's tabbed limited, and I'm not sure if the I'm going to use my server program, so I'm not sure if it can accept tabbed limited, but it's easy enough to find out. So first let me save this. Save. And let's call this somewhere. And I'll put my name on it, because this is my version of it. Hit the Save. And it should appear on the desktop somewhere. USA. So there's the data file ready. Now we would go to our server and go to the toolbox. Simple contour map. Oops, I must have a error there. Let's see, ID 10T. Hit the upload, it claims it's there. We can look at the file and let's look at it somewhere. Lowercase s. That's weird. It didn't seem to take the upload. Okay, file should be located at somewhere USA-cleveland.txt. Weird. I'm going to change the file name. Yeah, it totally did not take my upload. That is bizarre. Doesn't it know that I am God of this server? Interesting.
Could it be the file because it's not a comma delimited?
It's going to accept the file because it's a ASCII file. The program doesn't care until I try to run it. Let's try something else. SW. So the file's there, the browser just wasn't showing it. That is weird. And yet when I do that, So there it is down there. I don't know why it, and there's the other one. Okay, so it's the leading letter. Capital letters are bigger than lowercase letters. So the first file got there too. So let's go back and actually try to set the file. So the y-axis is feet north, x-axis feet east, map title somewhere USA. I think the first set of grid columns, so that's the x direction. Let's put about 60 in the x direction, 40 in the y direction. That's based on the shape of the original graphic. I'll start with smoothing parameters set to 0. I'll do quadratic weighting. I'm probably going to change a few of those, but let's go ahead and let it build our map. And there is our contour map. So it's picked up the appearance of that of the creek over here, which is low. Remember these x's are like in the 20s, 26 or something, and then it grades up to 70 over here. And so now we go ahead and we'll look at doing some smoothing. I'm pulled a number out of my datum. That's looking a little better, but let's to get rid of these pits down here, I'm going to see if I can't increase the weight of stuff that's further away. I'm liking that. Now that's a okay contour map. And so now you have pretty much what you need for this. So 70 here, 65, 60, 55, and then down here in the bottom of the creek you're in the 30s and 20s. That would be a sufficient contour map to help you with both the drainage engineering and the water system design. I mean the drinking water design, because as you'll recall, your next exercise, there's going to be a pipeline system that's laid out on this area. And so you can use this map to figure out what the elevation of the individual nodes are. Let's see, make it large. Let's just see what happens when we make a really big number for the weighting exponent. I don't recommend you do this. Yeah, we kind of lose information doing that. So 1 to 3 are typical. I liked 6, so we'll stick with 6. Bump up my smoothing parameter to about 30. I usually do smoothing parameters half of the larger number of grid columns. Seems to make a nice map. And I like that map. That's the one I would use. And then the next step would be we want to capture that. So organize my capturing software. Oh, I guess something like that'll work. And if it was going to work, it would work. But naturally, okay, hit capture. There we go. And I'll save it to documents. Go here to documents and WTF. Should have the one I just captured. Interesting. One more time. Huh. This thing's just not working right all of a sudden. I don't need this picture anymore. I know I have the database already built, so I will cancel that. I will shut down the Windows machine. And other than not being able to screen capture it, that's 75% of the problem set. Okay, it can be shut down. There it is. So there's the screen capture. The next step would be to do some internet reading. Why does it do that? Because it's a computer. And Nico, can you get out of the way? Just sit down. Just sit down. Wait, how'd you get out of your cage? That makes no sense. Another break. Where was I? Okay, so we have the screen capture. Next thing we want to do is read how to make transparent background. And then do some reading here. Depending on what graphic software you have, there's different ways to make transparent backgrounds. So for example, the one I'm rendering the picture in is called Preview, and I would watch this YouTube video and follow it to make the background. But I've lost the desktop I was at a while ago. So that's how to do ES2. I don't want to save it there. Okay, so that's how to do that, and if I could actually find the image again, but it keeps doing this to me. Downloads go away, screenshot, ta-ta for now, bye. Get back to the other desktop, and now get the screenshot. Right here. So in Preview, I think I'll go to Markup and choose this guy. And I can make that area transparent, then I can make that transparent, then that. And it's, you know, it's admittedly a bit of a nuisance, but you can transparent most of the background. And then once that's done, you save that image, and then you can overlay it back on the original drawing. And now you have a contour map on top of your base map. And that was the exercise 2 task. So, and there's equivalent functionality in Windows-based software. So you don't have to use a silly old Macintosh to do this stuff. We'll now go into, see, we've got 6:30, 7:30. We can go into the notes pretty quick, so I'll give a quick overview. If you watch the morning lesson, you have a longer detail on what's in here. So this lesson is dedicated to pipe hydraulics, and we've seen this picture before, and this is just an example of using what online tools we have to find the flow between two reservoirs. In this case, we're going to change the materials, and we're going to include the entrance, and the exit loss coefficients. So to do that, we'd want to go determine the roughness height for the pipeline based on it being made out of ordinary concrete. And again, back on our toolbox, in Material Properties Databases, we have a roughness height database, and we can select ordinary concrete, submit the query, and it tells us that the roughness is 1 millimeter, which is the same picture as here, just a different date. We can convert the millimeters to feet using the unit converter tool. And everything I'm doing here you can do elsewhere on the internet. You don't necessarily have to use these tools. So we want to feet. .003 feet is just shy of 1 millimeter. And I think I'll put an 8 there. .0033 is a millimeter. And then, so we would use that in the online calculator to produce a head loss and a flow rate estimate. Next thing we want to do is look up the kinematic viscosity. We do that again back on our toolbox. That's a fluid mechanic property, liquid water, 50 degrees Fahrenheit. And there's the kinematic viscosity, 1.41 times 10 to the minus fifth. And then finally, the minor loss coefficients. If we go to the water distribution system's reading, here, partway into the reading, there'll be a table of loss coefficients for different fixtures and fittings. I think it's coming up on the guitar any second now. I bet I just ripped past it already. Relative roughness, Maisie-Williams, loss coefficients. So that that excerpt that's in the PowerPoint comes right out of this, and most of the other hydraulics books you have similar tables. The thing just resized itself. Turn to the notes. So we're right here, and from that table we would conclude that the inlet loss has a K value of 0.5, the exit loss has a K value of 1.0, and now we have everything we need to attempt this using the online tool, or we could write a Jupyter Lab tool ourselves, or we could do it in a spreadsheet, which is on the server, or you could do it by hand. We use the online tool because I have it already set up here. And if I make the following entry items, pool elevation for the left pool of 20 feet, right pool set it to 0, pipeline length of 10,560, which is 2 miles, 2 foot diameter, sand roughness height 0.00328. We took that out of the database. Kinematic viscosity 1.41 times 10 to the minus fifth. Gravitational acceleration 32. Inlet loss of 0.5, exit loss of 1. We'll ignore any fitting losses, but we do have to enter zeros to get it to work. And here's the output. And we'll go ahead and run that live right here. In pipeline hydraulics, we have flow between two reservoirs, no pumps, US units. So 20, 0. Pipeline length. Fitting loss, set that to a 0. An actual 0. There we go. Pipeline diameter 2. Fitting loss 0. Roughness height 0.00328. 1.41 times 10 to the minus fifth. 32.2. And so now we're ready, and what it's going to do is take that information, it's going to apply the Swami-Jain equation on that pipeline. It's going to use that to get an initial estimate of flow, and then it's going to use Newton's method to refine that estimate, including the losses for the inlets and the exits and the fittings. That's all it's doing. So it's a first guess and then some modifications to handle the inlet losses. If you're doing it by hand, you don't have to do Newton's method because, well, you would trial and error the answer anyway. So I guess you are doing Newton's method of some sense. And when it gets done, it says that there is 10.2 cubic feet per second flowing in this system. let's see what we got here, 10.2. We should get the same answer. It's identical input. The same thing can be done in a Jupyter Lab notebook, but we'll skip that because Engineering 1330 is a brand new class, and so there'd be no way that any of you all could have had it yet, since it hasn't happened yet. And the second part is we can use tools like that, and we can break our hydraulic system up into pieces, analyze each piece, and then join them back together. And what that does, it gives us the luxury of being able to simplify an analysis by using pre-built tools. So one I'll demonstrate in a second could be done completely as a single system, but it would be a little bit harder because you'd have to do it more or less by hand. The idea is to break the system into independent or separable parts, analyze each parts, and then reassemble to answer questions about the whole system. Let's consider an example. So here's a pipeline system that takes water from Lake Gulameta, pumps it uphill to this large diameter tank here, and then from the large diameter tank, water is distributed down several different lines, and one of them goes to this storage tank that's in a schoolyard. And there's a drawing of the storage tank up here. And the advantage of this in this community is prior to this pipeline being built in place, this was done by Texas Tech students a few years back. They had to walk several kilometers a day to acquire drinking water. And so this has been a huge benefit for the health of this particular community. You can't tell it from the picture because it looks pretty desolate in this particular photograph, but there's a lot of cattle and wildlife out here, so the pipelines have to be buried somewhat deeper than is usually done. So anyway, some Texas Tech students, a few summers ago, I think 4 or 5 years ago, they actually assisted with digging the trenches, laying the pipe, and doing the solvent welds and welding up the pipeline after they essentially designed it and then got all the parts shipped into the country. Okay, so continuing on with our actual story. So this is Lake Gulameta at 975 meters elevation. Goes into some pumping system, which is at 965. So 3 meters below the top of the lake. It's almost 10 foot ahead. And then the pump pushes it up a 3,200 meter pipeline and discharges to the top of this tank at an elevation of 1,006.3 meters. The bottom of the tank is located at elevation 1,000.3 meters. Then one of the delivery lines goes through a valve and goes along this 800 meter pipe, comes up and drops into the schoolyard tank. And then here's some rough drawings to get the different heights. So the outlet valve on the tank is 2 meters. It's 6 feet. That seems a little high to me, but that's how it was originally designed. And then this is probably connected to another valve down here so that the school children can reach it and turn on the water. And so one of the things we'd be tasked to do in a design of such a thing, so drawing the lines and drawing pictures of tanks is pretty straightforward from a design standpoint. But we want to test it, and this is the whole point of hydraulics. We want to test the conditions that can happen on a piece of paper in the computer before we actually build it to help determine, in this case, what kind of pump to buy. So here's some of the things that can be anticipated. The float valve at the school tank could fail, and that float valve is up here. And so if that fails, water just pours out of this tank, it overflows, and we want to know what that flow rate is. The outlet valve, this valve could accidentally be left open. In my opinion, that's the most likely thing that will happen in this system, is the valve will get left open from time to time. The pipe could break. A pipe break here is critical, but it's not of the same nature because we still got 6 meters of water to work with while this one's repaired. But if this pipeline breaks the gravity flow system, there's no way of, we have to be sure we have enough water supply until the leak is detected and it gets fixed. So those are the 3 main failure modes. And one thing we want to find out is what's the pump operation requirement under the worst failure mode. And as this example proceeds, we're just going to go pick a pump. The other question to answer, which we won't answer tonight, is if the pump fails, how long until the system fails? System failure meaning you can't get water out of here at the schoolyard. We have some time because we got 6 meters of water up here, and the bottom of this tank is higher than the top of the schoolyard tank. So this big tank can be completely drained. And when it's empty, then the system has essentially failed. We have a little storage here, but not enough to make a big difference. So those are kind of the questions to be asked. So let's ask the first one. Suppose the float valve fails at the schoolyard. So that's simply 2 reservoirs connected by a pipe. We actually already have a tool to do that. The upstream head is 1,006.3 meters. The downstream head is 992 meters, right at the schoolyard overflow. There's 2 bends here and here to bring water from the ground up into the tank. If we look up the values for loss coefficients, their K values 1.5 each. There's an inlet K of 0.5 up at the big tank. There's an upstream valve, which is normally open so that everything works, but it has an isolation valve, which is good because if the float valve fails and you can make a phone call up to the top of the hill, someone can close the valve and at least save the water. So that valve has a loss coefficient of 0.15. And the float valve, if we look that up online, we'll find that a float valve, it's actually a pretty high loss hydraulic component, and it has a loss value of 70. Looking in our water database, we find out the viscosity is 1 × 10⁻⁶ meters squared per second, and the roughness height of high-density polyethylene, which is the pipe that's used, is 0.007 millimeters or 0.000007 meters. And at this point, we have all the information we need to go ahead and use our hydraulic model tool. So in this case, we would enter 1,006.3, 992, put the inlet loss, exit loss, we'll just use the float valve loss coefficient there, the fitting loss, and then the other fitting losses. So this is the entrance. This is the loss of the isolation valve fully open. And then this 3 is the bends, the 2 bends in the system. Pipeline length, 800 meters given. Pipeline diameter, 0.127 meters given. Sand roughness height converted into meters is that rather small number. Kinematic viscosity looked up in a database, 1 × 10⁻⁶. Gravitational acceleration, 9.8. Hit submit, and it does the calculations and computes about 16 liters per second, which is not a small amount of water, certainly not in that arid climate, as indicated by the picture, would be lost if the float valve fails in the open position and it can't shut itself off, which means that the tank overflows. Continuing on with the example, let's look at the next situation. Suppose the outlet valve is left open. One reasonable design approach is to just recognize that that tank at the schoolyard is just a circular tank with a hole in it where the valve is. And we could apply that information and set the outlet diameter of 0.05 meters, which is about 2 inches. The tank diameter of 1 meter was given. The water depth in the tank was 1 meter, which was given. Set a discharge coefficient of 1 just to use the Bernoulli equation. And the gravitational acceleration 9.8. And we come up with about 8 liters per second, actually almost 9. But 8 liters per second is the discharge rate under those conditions. Now, it won't sustain that for very long if the tank doesn't keep refilling, but if the float valve's working, as this drops down, the float valve will open and let more water in. So conceivably, we could lose 8 liters per second with that valve left open. I think that's the most likely situation that could happen. So we use information like that to try to establish some pumping requirements. So if the float valve fails, we know we need to be able to deliver 16 liters per second to the big tank from Lake Gulameta to keep the big tank full. If the outlet valve is left open, we need 8 liters per second. And if the pipe between the big tank and the schoolyard tank fails, we'll roughly get about 24 liters per second of discharge if there's a pipe break. So we're looking for a pump that can produce at 24 liters per second at least 30 meters of head, because that's the difference in elevation between the uphill tank and Lake Gulameta. And I've intentionally ignored pipeline friction to just go and do it as a common mistake, and we'll find out that we can't make these deliveries. But let's suppose this is what we think we need. We need 30 meters ahead at 24 liters per second. And so we would go search the internet and try to find a pump that can deliver that. And it turns out that the Kirlos-Skar KLS 1537 can produce 28 liters per second at 30 meters of head, which is not a shabby amount of head or a shabby amount of water. I mean, that's almost 100 feet of water, and 28 liters per second, I don't know what that is in gallons per second, but it's too much to drink. So that looks like that might be a usable pump. We can include the fittings that are going to be used to make the pump that has 100 millimeter inlet and outlets fit the 127 millimeter pipe that we're going to use. And if we do that, we can use a different tool that includes the pump. So let me go to that. Pump flow between two reservoirs. So I used this earlier today, so a lot of the data is still maintained in the input form. So I'm just going to I think it's that one. Okay, that's the fitting loss. That should take care of the fitting losses, and this is 0.0. that one. So that's most of the pipeline system. Now we have to specify the pump behavior. We'll study pumps more in our next meeting, but there's this particular simulation uses a 3-point pump curve to fit a parabolic curve to the pump equation and try to satisfy the hydraulic conditions. So we need shutoff head. If we look back on this table, shutoff head is not explicitly displayed, but we can see as we're moving up in meters of head, we're going down in pump rate. And somewhere out here at about 40 meters ahead, I would imagine, is where the system shuts off. So we'll go ahead and put 40 meters for shutoff. And we have some other points on the pump curve. So at 30 meters of head, we have 28 liters per second. So at 30 meters ahead, we have 28 liters per second. And one more point, let's go here at, it looks like that's 36 liters per second at 14 meters ahead, but that's a pain in the butt. Let's do 20. So we got 35 liters per second at 20 meters ahead, 20 and 0.035. And we're ready to do the simulation. So what this will do is this pump will adjust to try to satisfy the hydraulic conditions dictated by the pipeline fittings parameters. And we think we're going to deliver 24 liters per second, but we're about to get a shocking surprise. And that shocking surprise is 19 liters per second. Do I have a mistake? 34 meters of added head. Cool. Well, that didn't work. Oh, it's got to be the head differences are different than I had before. I think I have something wrong in the head difference. So this is producing 19 liters per second, although we want 24. So let me go back and see the mistake I made. 975. 992. Yeah, I had way too much head. This should be a 975 to agree with the problem statement. And now the shock. Whoa, even better. Well, oh, I don't have all the loss coefficients included yet. So I need to include the confuser and the diffuser loss. So that's the 0.51, 2.55, and 0.32. And if I do that, 0.51, 2.55, and 32. Once I start to consider losses, that's cool. It still is not the answer I'm expecting. 80, 60, 28. Oh. 40, 30, 14. 40, 30, 20. Well, that's weird. We'll go with what's coming out of the computer right now. So it claims we can do 22 liters per second. So this pump under this specification actually will do the job. The example I have in the presentation, I have some other piece of data. Static lift is wrong. And it's because I want to go from 975 to 1006.3. I'm going uphill, otherwise what would be the point of the pump, right? Now when we run it, we get the shocking 7 liters per second, which is enough to satisfy the school valve being open, but not enough if we want to handle other conditions. So some of the options we have, in all likelihood, if we really wanted to deliver that 24 liters per second, we'd go find another pump, a bigger one. But we can investigate the possibility of putting 2 pumps in a series. And that's pretty easy because when we put 2 pumps in a series, the added heads simply double. So that 40 becomes an 80. That 30 becomes a 60. That 20 becomes a 40. And we now get 17 liters per second. So you could argue that 2 of them in series almost works. We could try 3 in series, which I'll just show the next screen. I won't do it. And if we find 3 in series, gets us pretty close. But you wouldn't normally put 3 pumps in series in a lift station in a remote part of Africa to bring water to that particular system. You would instead use a larger pump if that was necessary. And that's the last of the slides. So the one comment I have is the single pump produces 7 liters per second, which is about all we need if the schoolyard valve is left open for any duration. And so that will work fine. And the other 2 faults, the float valve failing, a pipeline break, that's going to be a major interruption of service. And that would probably be, well, that was what was designed. So the actual design can handle the valve at the delivery end being left open unintentionally, but the other 2 faults, you have to shut the system down and repair it, which is typical. We can't build this stuff completely fail-safe or idiot-proof. There's not enough money in the world to proof things against everything that can go wrong. So that concludes the call. I went a little long today. I apologize for that, but you now have a pretty good guideline of how to do exercise set 2. And whoever chimed in earlier, if you feel you've done it incorrectly or you want a second shot at it, go ahead and attempt to upload it again. If it rejects you, just send me an email. Okay? Well, thank you everybody for your attention and patience, and have a great evening. Have a good day tomorrow. Stay safe. What's all the other stuff we're supposed to say on these? Wear your mask. Don't get sick. Just be careful and take care. And I will see you on Thursday. I'm fixing to shut everything down, so if you have any questions, now's the time to unmute yourself and ask, or I'm about to disconnect. Okay, very good. Goodbye, everyone.